Hello students, welcome to the class. So today we'll see the theory part 4 of the chapter chemical bonding and molecular structure. Our today's aim would be to cover the section 4.4. This is the disclaimer. Our objective would be in the section 4.4, and apart from this we will cover one more thing, so that would be a bonus topic for you, I guess. So that objective is drawing resonating structure and comparing their stability. Okay, so this will be the last topic we will discuss regarding the resonating structure. I've put up this here because it's very important, and it's important both in organic and inorganic. Questions are asked from here. You are asked to compare the stabilities of different resonating structure. So I will try to give you a very simple and efficient manner to do the same. Then we will cover the whisper theory. So I will focus mainly on the postulates today. I will not use it to say predict the shapes, but I will try to explain the basics behind the whisper. So how does whisper works, and what are the assumptions whisper theory makes to predict the geometry. If I say according to the NCERT, then of course we are doing the part of drawing resonating structure and comparing stability. And in the whisper theory, we are covering the NCERT section 4.4. Now we are not covering it wholly. We are not looking for the structures right now. As I have told you, we will only see the postulates. So the main postulates of the whisper theory can be written as what is being assumed in the case of whisper theory. So the important thing about the whisper theory is it only covers the electrons present in the valence shell. Similar to the Lewis theory, it is also concerned with the valence shell electrons. Now you know it, around an atom or around a molecule, there are bonded pair and non-bonded pair. Here, by non-bonded pair, I mean lone pair. We have seen this thing, what is lone pair and what is bonded pair in the Lewis theory. The participating electrons in the bonding are called as the bond pair. The non-participating electron pairs are called as lone pairs. Now we know that if there are electron pair present around the central atom, then of course they will repel each other. Now what is the meaning of repel or repulsion? To understand this, let us take a hydrogen molecule. See, we have two hydrogen atom. If they are about to make a bond, they will come closer to each other. In this process, we will see that when their proximity is decreased, then the repulsion is increased between the electron and electron of both the hydrogen atom. Now, apart from this repulsion, there are many more kind of interaction that will go on inside this say molecule, but whisper is mainly focused upon this repulsion part only. Okay, so two things are there that I have told you in this discussion. First is that the shape of the molecule is decided by the valence electron, and we know that the valence electron are present in two ways. According to the Lewis theory, it is bonded and non-bonded. Now we are about to keep this bonded and lone pair electron in such a pattern so that the repulsion can be minimized. We know that as they are coming closer to each other, there will be increase in repulsion, and when there is increase in repulsion, the energy of the system increases. But we don't want it so. We want the energy to go down. So what we will do? We will keep the negative charges at a maximum distance from each other, and we will show the electron pairs, whether lone pair or bond pair, with the help of spheres. And why are we keeping them at a maximum distance? To minimize the repulsion, okay, and to decrease the energy of the system. Let us consider an example of a molecule. Say we have BeCl2. Now there are two configurations possible for BeCl2. In between these two configurations, there are multiple configurations, but I have taken the extreme cases, right? So in the first case, if you look here, then the electron cloud are present at a maximum distance from each other. And this arrangement is having an angle of 180 degrees. Okay. In the next part, what I have done, I have kept this two bonded pair. Of course, these are the bonded pair or the bonded electron cloud because it is present between the beryllium and chlorine, right? If we are to bring this 2CS closure by decreasing the angle, okay, so this is the maximum angle possible. You can't take any angle apart from this. If you will try to stretch it more, then it will go to a lower angle and the repulsion will increase, as is the case here. So if you take them as 90 degree, the repulsion has been increased because we know that the repulsion and attraction force in the electrostats are very much dependent on the distance between them, and here the distance between the negative cloud is decreasing. So this is the basis of the valence shell electron pair repulsion, and the name is coming from this thinking only, that we are about to minimize the repulsion because your electron pair, whether bonded or lone pair, they repel each other. Now the question arises, what is the extent of repulsion? And do the lone pair and bond pair do the same kind of repulsion, or there is some difference? So we have to understand that. Okay, for that, let us move on to the next part of this postulate. I hope this is clear to you, that why are they kept at an angle of 180 degree. Now this is just an illustration. We are about to predict the geometry and shape of each of this in the next class. But for now, you must analyze that why are we keeping in such a manner. And the basic reason is to minimize the repulsion. Okay. So what is the next postulate? So this is the most important one, and that is you are to consider the multiple bond as a single electron pair. Okay. Yes, but one thing is very obvious, that if your multiple bond is present, that means you are having a very high electron density, and in that case you will call it as a super pair. So super pair means simple, high electron density. Again, I am repeating it. So if you are considering the shape, right, suppose in place of BCl2 we have the CO2, right? So the carbon will be attached to one oxygen with a double bond, and to the other oxygen with a, again with a double bond. Now the shape of the CO2 will be linear, and the shape will not depend upon the double bond here, although there are two double bonds, and in the case of BCl2 there were no double bonds, but still they have the same shape. So remember this very important point, that your multiple bond is always treated as a single electron pair, but they have a greater repulsion, and that is the reason they are called as super pair. If I want to illustrate the same with the help of a diagram, so say we have three electron densities. The first is for the single bond, the second is for the double bond, and the last one is for the lone pair. Now what is the difference between these three? In case of the single bond, the electron is shared between two atoms, right? So in a single bond there are two electrons, and those two electrons are shared between two atoms. As a result of this, your electrons of single bond are stretched, okay, and due to this large area coverage they have a low density of charge. But as soon as you come to the double bond, so here I have shown these three electron pairs with the help of different intensities to show that how the density of charge is increasing or decreasing. In the second case, if you see, then it is a double bond. Now here also the electrons are of course you can say distributed between the two atoms, but here we have four electrons. So if you consider a double bond, in the case of Lewis structure, if you remember, across a double bond, four electrons are there, right? So due to this extra number of electrons, it has a greater density as compared to the single bond. But if you consider the lone pair instead of that, then in this case, your electrons are not between two atoms. It is on a single atom. Take the example of water. If you see here, the lone pairs present on the oxygen is only on the oxygen. It is not distributed between oxygen and hydrogen. Okay. So due to this localization of the electron on a single atom, the lone pair or the non-bonded pair have a very high charge density. So this is very important to note down here, that your charge density is increasing from single bond to double bond and double bond to the lone pair. But in our today's discussion, I would be only focusing upon the repulsion between the lone pair and the bonded pair. So let us try to give an order to the same. So the shape are predicted by the whisper theory for different resonating structures are same. Now what is the meaning of this? So here is a figure for you of the carbonate ion. If you look at these three carbonate ions, then these three carbonate ions are resonating structure of each other. They are figured as 1, 2 and 3. But if you look at the shape for each of this, then all of them have the same shape. And I guess it is quite clear from the diagram. So we can say that whisper theory is not differentiating between the resonating structure. It is giving the same shape for all of these three resonating structure, which is named as 1, 2 and 3. So you can think of more resonating structure. Say we have the ozone. So ozone also have three different resonating structure, and those three structures will have the same shape. Okay. So I guess it has two resonating structures, not three. It has two resonating structures and both of them have the same shape. So this should be always be in your mind. So same thing is being written here, that all of your resonating structure of the carbonate have the same shape. That means your arrangement is same. So your carbon is present at the center in the first structure, in the second and the third, and your three oxygens are present at the trigonal corner of these three 1, 2 and 3 structures. Okay. Now we have looked upon all the postulates of the whisper theory. Now we have already seen that there is repulsion between the electron pair, and due to that the bond pair and the lone pair arrange themselves to give the minimum repulsion. Now the arrangement is based upon the repulsion, so we have to give an order for different kind of repulsions that are possible. This theory that I am discussing right now is very, very important, because nowadays questions are asked from the theoretical part rather than the outcome part. Okay, so you may be expecting a question from the shape and structure of the species, but you can get a question from the postulate. It will be an easy one if you know the concept behind each and every postulate. Okay, and you will easily get your number without any much stress. Now let us look at the order of repulsion. So the repulsion order for the different pairs can be written as, first of all, the maximum repulsion is shown in the case of lone pair and lone pair. So if you are seeing two lone pairs, then they will have the maximum repulsion. Okay. Then second one in the repulsion order is the repulsion between the lone pair and the bond pair. And the third one is between the bond pair and the bond pair. Now let us look at the same with the help of a pictorial representation. So here we have the first case where we have two lone pairs. Now as the lone pair is considered to be the highest charge density, therefore it is being shown with the help of a thicker area. Okay, so you can look at these two lobes, which is representing the area of the electrons effect, and both of this area are quite broader. So as a result, since their area is broader due to the high charge density of lone pair, Therefore, they will do the maximum repulsion if they are closed to each other. Okay, if they are close to each other. So what you will do in this case, both of these lobes will try to move away from each other. In the second case, we have the lone pair and the bond pair. So this stretched one, if you see this oval, this is the stretched one, okay, and this is the flattened one. So this stretched oval is signifying that your charge is same, but it is being distributed over a larger area. Okay, or you can say it is not onto this circle, it is away from this circle. As a result of that, the repulsion between these two lobes will be lesser. Okay, in compared to the lone pair and lone pair, this lone pair and bond pair will experience less repulsion. Now, it can be easily seen in this diagram also that the spacing between these two pairs is very less. But as soon as we introduce a bond pair, this spacing is being increased. And if you replace the remaining lone pair again with a bond pair, then the spacing is further increased to a greater extent. That will result in a even less repulsion. So what we can say from this diagrams, that due to the large lobes, or you can say the high charge density of the lone pair in a small area, the area of impact of the lone pair is more, due to which they show more repulsion, and hence we are seeing greater repulsion in case of lone pair, or lesser amount of repulsion in the lone pair, bond pair, and the least amount of repulsion in the bond pair and bond pair. Okay, I hope this part is clear to you. So just try to think over it. So this is a very important reasoning behind this order. So you must have seen this order, and the reasoning is very perfect. Now coming on to our bonus topic. We have already seen the postulates of the whisper. In the next class, I will try to discuss the outcome of this postulates, as well as I will look at the method used to describe the shape and geometry of different molecules. Now that is a very different part, and of course questions are asked from there, but you should be looking at the theories as well. It will help you to remember the outcome part easier. Okay, so if I now move on to drawing of the resonating structure, then first of all, let me introduce you to the various types of resonating structures that are possible. So here is a table for you. Okay, what is this table depicting? It is depicting you the types of fragments that can show resonance. What are those types? The first type, if you look, it is a double bond, single bond, and a double bond type fragment. Okay, so this fragment is capable of doing resonance. Now be with me, try to just grasp that what kind of fragment I am trying you to show. You can take a notebook and try to draw the same, so that will help you a lot. But you should at least remember that what are the types of fragments that are capable of doing resonance. The second fragment, if you look, so it is like this. So there is a lone pair here, then a single bond, and then a double bond. You can see the same in this resulting structure or the example structure. There is lone pair on the nitrogen, then there is a single bond between the carbon and nitrogen, and lastly a double bond between two carbons. Okay, then coming on to the fourth structure, I will move on to the third structure later on, because right now you are not aware about this radical and all, so I will not teach you about this right now. So it is just for your knowledge. In case you need it in the later on classes, you can use this same resonating structure concept. Okay, so I'm leaving this part. Now coming on to the next one, we have a positive charge, then a single bond, then a double bond. So this fragment can also show resonance. And lastly, we have a negative charge, then a single bond and a double bond. Now what you can observe from here, there is a very general trend. Okay, so there is a single bond everywhere between two electron sources. What are the electron sources? If you look at the first one, then the double bond is the electron source, and between these two electron source is a single bond. What is the next electron source? In case of the second image, of course, one is the double bond, one is the lone pair. In between, again, we have a single bond. But in the fourth one, if you see, then there is a electron sink where the electron can go. And on the left side, we have the electron rich species or electron donating species. But in between, we have the single bond. So this is the general pattern that we see. So either there will be a set of electron giving species across a single bond, or it can be a taking species or giving species across a single bond. Two possibilities are there. Out of this 5, 3 are of the electron donation, single and electron donation, whereas 1 is of the electron donator, single and electron reservoir, where the electron can be stored, the positive charge. So these are the fragments that can show resonance. Now let us try to understand that how they can show the resonance. First, let us take this double bond, single bond and double bond type of fragment. Okay, so this is our fragment. What can be the possible resonating structure for this given structure? So your double bond that is present here, okay, so this double bond, this can just hop from the left side onto the single one, and at the same time this double bond will hop onto the right side carbon. Now you can show the same with the help of an arrow. So it will go in this fashion. This will move here and this one will move here. Or you can do it in the opposite direction also, because both of the direction are symmetrical. Okay, the molecule is symmetrical. You can move them in either of the side. Now what will happen? As this electron pair or the bonded pair is moving away from this carbon, therefore it will have a positive charge, whereas the electron source is moving on to the left extreme carbon, so it will have a negative charge. Right? Is it clear? So it's very easy to understand. Now if you look at both the structures, what you can see? You can easily say that the position of the carbon is not at all changing. Okay, only the electron pairs are moving from here onto there. Now here is a task for you. Just try to draw the resonating structure for this second species. What will happen in this second species? Any guesses? So there is a lone pair, then a single bond and a double bond. So it is the case for the second type of fragment. Remember student, the electron will mostly flow from a density of high charge area to a density of low charge area, and we know that the high charge is on the lone pair, so the electron will flow from the lone pair onto the left hand side. If it is so, then what will happen? How will the electron move? Any guesses? Will it move from the nitrogen to the carbon or from the carbon to the nitrogen? Again, I am repeating my part. So you have two types of electron sources across a single bond. The first one on the left side is your double bond between two carbons, and the right side we have the lone pairs or nitrogen. I said you that electrons will always flow from a higher region to a lower region. Yes, the electron will flow from the nitrogen. Okay, it will move on to this and then it will move on to the next carbon. Now that will create a charge on each of these species. So if I ask you that what is the charge on the nitrogen and what is the charge on the carbon on which the electron has now moved, then what will be your answer? As the nitrogen has lost its electron, okay, whereas the extreme left carbon has gained some electrons. So the nitrogen will obviously develop a positive charge, whereas your carbon will develop a negative charge. So just take out your notebook and try to draw it by yourself. So I am leaving this next resonating structure for you. So just try out this. Meanwhile, I am moving on to the next type of resonance, which is what? Which is double bond, single bond, and radical. Now I will not tell you much about the radical. I will only show you the electron movement. Okay, so I'm not depicting it about it. Okay, in the bold fashion. So the next type of resonating structure, as I said, is your double bond, single bond, and this lone. Okay, not lone pair, radical. How it will move? So there is a very small twist in this, right? The movement goes like this. It moves on to here, and this bond moves on to here. But in this process, we use a single hooked arrow. Now this is an important part of organic chemistry. I'm telling you here because I'm trying to teach whole of the resonating structure right here. Okay. Apart from the energies and all, I'm trying to teach about the basics of it all. So if you look at this structure, I have used half hooked arrow. Now what is the meaning of this arrow? The meaning of this arrow is that only single electron is being moving here and not a pair of electron. Okay. So that is the reason I have resembled it here with a single hooked arrow. Okay. Now what will happen? One of the electron of this bonded pair will move on to the carbon, and that will create a radical on the carbon. But your bond here, which is being broken and moved onto the carbon, contains two electrons, and one of these electron is still on this middle carbon, and one of these is being moved on to the next carbon. Now this radical, which is coming on to the bond, and the remaining radical of the middle carbon will join together and make a complete bond. Is it clear? Again I am repeating it. What is happening in this process? Your radical is moving and moving on to this bonded area, and this bonded electron, the double bond, is moving, but only the single one is moving on to the carbon and making a radical. Now the electron that is left on the middle carbon, it combines with this radical to make a double bond. So this is the next resonating structure for the given radical. I hope this is clear to you. Now next we have the example of a double bond, single bond, and a positive charge. How we will do it? If I ask you that your electron will flow from high density area to a lower density area, then what would you expect from this diagram, or what would you expect from the resonating structure of this diagram? From where will the electron move, and it will move on to where? Just think about it. It's very simple. You know where is a high charge density and where is a low charge density in the given species. You know that your positive charge is representing the low charge density area, and your double bond onto the left side is representing the high charge density area. If this is so, then your electron will move from left to right. Okay, it will move on from left to right. So we can show it here. This double bond will move like this. Okay, and that will create a positive charge on the first carbon, whereas the positive charge on the right carbon will be neutralized by the double bond that is being moved on between the carbon. I guess this is clear to you. Okay, so this is the fourth type of resonating structure. Moving on to the next, which is double bond, single bond, and negative. Now again here, students, the high charge density area is being shifted from left onto right because the negative charge represents a much more high charge density. Therefore, the electron will move from the right onto the left. Got it? We have seen it that the lone pair has a greater charge density. If that is true, then your lone pair will move like this, and the double bond will move on to the extreme left side carbon to create a negative charge on that carbon. So with this, we have understood that how do we draw the resonating structures for different type of fragments. Now I will use all of this to do some examples of organic species where the resonating structures are being shown. So let us try them. So the next topic would be the flow of electron. From our previous discussion, it is very clear that your electron density is always moving from a higher density to a lower density, or from a higher electron area to a lower electron area. If it is so, then let us work on some examples for the same. So this is your first example. Just take out a notebook, try to draw the curved arrows with me. So there are tricks for doing this. I have already told you about them. So that is learning about the fragments. But the major part of drawing the resonating structure is to practice this thing. It's very, very important to try and draw the resonating structures by yourself by using the curved arrows. So that is the most important part of drawing the resonating structure. And believe me, this will help you a lot in your organic chemistry if you know this thing of rotating the arrows. It's very, very important. Okay. There are chances that you won't be able to draw this by yourself, but I have tried to make it as simple as possible. Here is your first part. So what is the possibility of electron flow? We know that electron flows from high charge density to a lower charge density, and this lone pair on the sulfur carbon is representing a high charge density. So the electron will start flowing from here, and it can move in the either side. It can move from the first, which is sulfur, onto the fifth, or from first to the sulfur to the second carbon. So that's up to you, because here no other substituent is present. It is totally symmetrical. The lone pair can move on either side. I am moving it in the right side. So here your lone pair is moving, and it is going in between the sulfur and carbon, means between the first and the second connectivity, and that is making a double bond. As your lone pair is moving away from the sulfur, it is creating a positive charge on the sulfur, whereas this bond pair will move on to the next carbon, and that will create a negative charge. We have already seen this kind of resonating structure in the previous part. Okay, if you know the way of drawing the fragments individually, you can apply all those fragments here, or some of those here especially, to draw the resonating structure. If you look at the second resonating structure, then it is on the next part. If you see, then here is a negative charge, a single bond, and a double bond. Now, do not ever move the electron back onto the side from where we have started. So you can see that the negative charge is on the third carbon. You can move it in the right direction also, but here, if you will do so, then you will get back the first resonating structure back. Therefore, you will move it in the forward direction and not in the backward. Negative charge moves further, and that again create a negative charge on the fifth carbon, which is here. Now, in the last part, I have done this same thing. I have rotated it, and it goes on rotating. Okay, so this is the resonating structure. Now, if you try this out and come on to the last diagram, then you can move this negative charge and get your starting structure back. Just try this by yourself. It's very fun to draw the resonating structure. Just take different examples. If you have phones, just look at the diagrams given in the phones, or much more examples as you can take it. Do it by yourself. Make diagrams, and it will help you probably to draw the resonating structure. Okay, and you will be far from each other. So let us move on to the next example. So I will give as much example as possible in this class, and I am leaving it up to you to draw the same and try some new by yourself, given in the NCERT especially. In the next example, we have the case of a lone pair and a double bond again. You can see here that this lone pair is having the maximum density. So the charge will move here and create a negative charge on the next carbon. Again, this negative charge will move here and throughout it will go. Lastly, it will come on to this single bond such that the oxygen's positive charge has been neutralized. Now there is an important difference between the example 1 and example 2. What is that difference? If you look at the first example, then here your ring is having 5 members, or you can say odd number of members, right? As a result of this, you are getting 5 resonating structures. So remember this point always. If you are having an odd number of member in the cyclic chain and your electron is starting from the cycle itself, not from the outside, like in this case. Okay, so it is, if it is starting from the cycle itself, suppose in this case your sulfur is a part of cycle and the electron is also present here, then the number of resonating structures will be equals to the number of participants of that ring. Now this will help you to check your answer whether you have gotten the right number of resonating structures or not. Okay. In the example 2, if you look, then the electron is being moving and coming on back to the oxygen. Where is it starting from? Again, it's starting from the high charge density. Then it is moving on to the low charge density. Here we get a negative charge, again a low charge density, and then it goes on rotating and comes back to the oxygen. I hope the part of drawing the resonating structure is clear to you. So now I will suggest you to again try the resonating structure of carbonate ion. Okay. So I have already given you to do the same in the last class, and I will do that same exercise here also after this class is over. But for now, just try to make the resonating structure of carbonate and tell me that how many resonating structures are possible for this ion. Got it? Okay. Now moving on further. So our next focus would be comparing the resonating structure. So we are now dealing with the stability of resonating structure, that how do we compare the stability and what are the parameters that we will see. The first rule is regarding the number of pi bonds. Okay. Greater is the number of pi bonds, more stable is the structure. Now here is an important point. I will give you a series of rules. Okay. And you will follow those rules one by one. Try to follow them in a way that they are in the canonical order always. First check the first rule, then the second rule, third rule, and so on. Okay, so this is a type of priority order. If your resonating structure is being more stable according to the rule 1, right, then your structure will be more stable. You will not move on to the second rule. Similarly, if your structure is same for the rule 1 or the first rule is not applicable for the resonating structure, you will move on to the second rule. And if your second rule clarifies the stability between the two, then your structure stability is being obtained. So I will go through each of these rules one by one, and then I will move on to the examples related to the same rule. The first rule says that greater is the number of pi bonds, more is your stability. For now, you are unaware about this pi bond. So let me use a different word for it. Just simply count the number of bonds. Okay, as simple as that. Now the species with the greater number of bonds will be more stable. If the number of bonds is same in both of the species that you are comparing, then look for the octet rule. Okay, so how it is done? The one species which is having all of its atom as its complete octet, so that will be more stable one. Remember that the structure that satisfies your octet rule is the most stable one. Next is your charge. So if your octet rule is completed in both the structures, your number of bonds is also same, then you will look on the charge. Now what about charge? So the neutral structures are more stable than the charged ones. The fourth one is, if both your structures are having the same number of bonds, they all are having a complete octet, they all are having a charge species, then you will look at the charge placement. How? So the negative charge should be present on an electronegative element. If it is present on a less electronegative element in the one of the structures, and in the second structure if it is present on a more electronegative element, then the second structure would be more stable. And your positive charge should be a more electropositive atoms. So suppose you have a charge on carbon, and in the second structure you have a charge on nitrogen. Remember, both of these charges are negative. Then which species will be more stable? The species with the negative charge on carbon or the species with the negative charge on nitrogen? What will be your answer? Again, I am repeating my question. Just think about it and write it in a notebook. So you have two species. In one of the species, the negative charge is on the carbon. In the second species, the negative charge is on the nitrogen. So out of these two species, which one will be more stable? Of course, the species with the negative charge on the nitrogen will be more stable, right? And lastly is your distance rule. What is this distance rule? The distance rule says that the positive charge and the positive charge, or the negative charge and the negative charge, in simple terms, if I say that your like charges should be away from each other, whereas the unlike charges should be closer to each other, that will create more stability. So these are the 5 rules, and you should look at a structure's stability throughout by looking at each of these rules one by one. Got it? Okay, so let us look at an illustration that clarifies our first rule. As I said you, the first rule is determining the number of pi bonds. So if I have two structures and one has the greater number of pi bonds or double bond, then that structure would be more stable. And the second rule is octet rule, which says that all the species that are present within the structure should have a complete octet, and that would be more stable. But sometimes we give priority to the second rule instead of the first rule. In which cases, where your elements that we are considering are very much electronegative, like your fluorine, oxygen and nitrogen. So here is a illustration for you. On the basis of these rules, can you say that which of these two structures will be more stable? Structure 1 or structure 2? It's very simple. Now remember, first of all, that your electronegative elements cannot have an incomplete octet. If it is having so, you have to reverse the order of the rules. And those electronegative elements are fluorine, oxygen and nitrogen. In this case, it is not present. You don't have to worry about that. So you just have to compare the stability based on the number of double bonds. So which of these two species will be more stable? One number or two number? Just think about it. It's very simple. So I guess many of you are attending the class, so I would expect more answers from you, right? And I guess it's an easy one to see that how many double bonds are there in both of these structures and which one is having a greater number of double bonds. Okay, the first structure is having a greater number of double bonds. You can count it. It is 2 in the first and 1 in the second. So what can we say? That the number of bonds in the structure 1 is 8. So if you look at here, 6 bonds are present in the single form and 2 are present in the double form. Okay. So therefore, 8 bonds are there in total. Whereas in the second structures, 7 bonds are present. Therefore, we can easily say that structure 1 is more stable than the structure 2. Okay? Is it clear? So as soon as you see that the rule 1 is being satisfied, you will not move on to the rule 2. So this is a canonical order. You will follow it step by step. Now moving on to the next illustration. So this illustration is related to the charge. I have told you that the neutral species are much more stable than the charged ions. Therefore, what we can say that neutral species will be more stable. The second thing I said about the charge is that your negative charge should be present on more electronegative element. If it is so, then and then only your structure will be stable. Whereas the positive charge should be present on more electropositive elements. Here is an example for you. So can you just count and tell me that which of these two structures will be more stable? So start from the rule 1. Okay. Check it for the rule 1, check it for the rule 2, rule 3, rule 4, and then come on to the conclusion. Right? Go just step by step. Okay. Don't just hop from the first rule to the second rule. So that will clearly make mistakes. Now, if you look at these two structures, what we can compare? We can say that both of these are having the same number of bonds. What is the number of bond? So 6 is present in the ring and 2 are present outside the ring in the structure 1. Whereas in the second case, 7 bonds are present within the ring and 1 is present outside the ring. So therefore, here also 7 bonds are present. So what we can say? That they have the same number of bonds. Therefore, the rule 1 is not applicable onto them. Now, moving on to the rule 2. So meanwhile, you can just try this question. It's very easy. And tell me that what is the correct answer. Next, you have to look for the octet. Now I'm leaving this octet part onto you. It's very easy to guess. The oxygen is having 2 bonds, so its octet will be completed. The nitrogen here is having 3 bonds, so its octet is also complete. Okay. Now, let us move to the rule 3. Both of the canonical structures are charged. So rule 3 is also not applicable because it is saying that the neutral structure would be more stable, and here both of these structures are not neutral. They both are charged, right? Therefore, we will move on to the rule 4. If you look at the rule 4, it is saying that the negative charge should be on much more electronegative element. But in the structure 1, it is on the nitrogen, which is less electronegative than oxygen. Therefore, your nitrogen, which is having a negative charge, which will be more unstable. So we can say that here structure 2 is the correct structure. I guess this is clear to you. It's very simple to understand. All these 3 rules were not applicable. So you move on to the 4th rule, which says that the negative charge should be on more electronegative element. Now moving on to the next one, which is distance rule. So your positive charge or positive charge, I can say the like charges should be away from each other and the unlike charges should be closer to each other. Whereas it is written same, so the opposite charges should be closer to each other. Now let us take an example and try to compare the stability of these 3 resonating structures. So how can we compare them? So we will look on all of those rules one by one. If you look at the rule 1 and rule 2, then rule 1 and rule 2 both are same for these 3 structures. You can see it very clearly that they have the same number of bond, which is 10 in the first, and second also has the 10 bonds and third also has the 10 bonds. Therefore, these 3 resonating structure has the same number of bonds. So rule 1 is not applicable. If you look at the octet of also for these 3 structures, then these 3 also have the same number of octet complete atoms. Okay, so there is no element which is having an incomplete octet. So rule 2 is also not applicable to these three structures. But as soon as you look at the rule 3, then the structure 1 appears more stable than the 2 and 3. What is the reason behind it? Why is the structure 1 more stable? I've already talked about this. So rule 3 is saying that your charge species are less stable. Yes. Therefore, the structure 1 which is having no charge will be the more stable as compared to the 2 and 3. So we have already got our most stable structure. Now we will try to arrange the remaining two structures, right? If you look at 2 and 3, then they both are charged. So rule 3 is not applicable for these two. So we have to move to the rule number 4. Now rule number 4 is also same for both of them. The positive charge is present on nitrogen on both of these, and here it is present on the carbon for both of this. Okay. Although the negative charge is not present on a more electronegative element, but it is same for both, right? So this, in this way, your rule 4 also is not applicable to both of these species. Therefore, we will move on to the last structure, which says that the rule says that your opposite charges should be closer to each other. So if you look at the second and third species, they are having opposite charge, positive and negative in the second structure, and the third structure is also having the positive and negative. But in the second structure, the positive and negative charge are closer to each other. Okay, so fifth rule says that the opposite charges should be closer to each other, and in that case it will be more stable. So it is clear from the second point of the rule 5th that your second structure is more stable. So what can be said from here? That the opposite charges have a greater separation in case of third structure as compared to the second, and this increases the instability of the third species and increases the stability of the second species. I hope you got all the points of comparing the resonating structures and drawing it also, and also you got the basics of the resonating structure of the VSEPR theory. Tomorrow we will try to draw the shapes and look at the geometries of the structures with the help of VSEPR. Thank you for attending the session. I hope you enjoyed it.